It's not for just this audience, live as well. So, welcome to this session of ChemHistories at Tutorial College, where we are on our usual third Sunday of the month. First Sunday we are at Prithvi College, Prithvi Theatre, sorry, or Prithvi House, as may be the availability of the place. If there is a fifth Sunday, we have started in activity, which is live from our laboratories in the TI. Okay, the founders of ChemHistories, then you, me, and Himachal. Okay, great. So I have my partner in crime. He is the founder of this kind of activity in TIFR, not just ChemHistories, a lot of other office activities. I don't need to speak too much of it. I can speak for hours. Arnab is an IIT alumni, went to Wisconsin, came back to Germany, did a lot of work there, and his passion is community science. Let's hear from what Arnab has to say today. All yours, Arnab.
Thanks, Suren. Okay, online audience, I hope you can hear us. If you cannot, please put it in the chat. If you cannot hear us properly, both on Zoom and on YouTube. Can somebody be checking the chats on YouTube and something? Online audience, please tell us you can hear us, you can hear me. Before we start, just a reminder, December is a month where the Nobel Prizes are given, and the December ChemHistories we have some of the year. So, but before that, the first Sunday of December, 2 weeks from now, is going to be a talk about a little bit again history of the science in India in sort of the modern period, leading up to independence, etc. There's a very nice talk by Steve Raichaudhuri. He will be giving that, and the mid-December ChemHistories will cover the Physics Nobel Prize and the Chemistry Nobel Prizes. The Physics Nobel Prize is on quantum various things, optics, things like that, related to quantum information processing. The chemistry one is on zinc chemistry. So there will be 2 talks on that over here. And the biology talk, the medicine talk will happen on the first Sunday of January, which is January 1 actually, it's New Year's Day. And Prithvi will be the third Nobel Prize talk. Okay. So usually these days I try not to do too many sessions myself. Only when I can't find anybody, I step in. And so let me share my screen. This is the time to share the screen for the online audience. Wait, we need to go here. There. Full screen. Okay, so I hope the online audience you guys can see my screen, both on Zoom and on YouTube. And again, reminder, please put your questions and comments in the chat. Some people will get them and let me know what they are, and we'll try and take it either during the talk or at the end. People over here, I hope you can see the screen. Okay, so today is the time to tell you some stories about chemistries and ChemHistory of something which is maybe familiar, maybe not familiar. We'll check how much you know about it. A very simple substance called ammonia. Okay. And this was the poster title, and the reason I like this is I have to double click once here. Okay, is this actually connects from what I do in the lab, the left, we see, to what is happening in industry in a very large scale. I'm going to tell you some stories. I'm a story there. From the ancient times till today, there will be a good bit of chemistry that is going to be talked about, but mostly it's not so much on the chemistry, it's a story of people. Some people who are very famous and well known, everybody perhaps, some who are unknown, some who are completely forgotten. So there's a lot of history in this, there's also some mystery if you wonder about why things happened the way they did. Now, there are lots of better storytellers than me. There's lots of stuff available on the web. I am not a chemistry expert. I'm not a historian. These are things which I have read. I found interesting. I made a note of various things. If you look at the American Chemical Society, the Royal Society of ChemHistories, websites like chemistryworld.com, everybody has got lots of very interesting articles about the history of ammonia. Okay. In fact, there is a new source book that's available which is called Making Ammonia. It's a very recent book, 2022. I haven't read the book. There is longer. There is open source book, so I thought maybe. And as with everything, a little knowledge is a dangerous thing. I have only a little knowledge in this. So with that caveat, let's get on. Now we're going to start with a quick quiz because I need to know what you all know about ammonia. So I know where to pitch the top. So let's take a poll and I'll give some time for people or the online audience to enter in the chat box. Have you heard of gas ammonia? First, let's get the crowd here. You've heard of gas ammonia? Very good, very good. This is good. Okay, and have you smelled the gas ammonia? Yes. Where did you smell ammonia? In the lab. In a public toilet. If you have not smelled ammonia, just go down this corridor, go to the bench or something, go stand outside, you smell. Go to any railway station or anything, you stand outside the public toilet, you will smell ammonia. The gas will smell is ammonia. The smell is ammonia. Okay. You can ask me why it smells, I'll answer that later. Are we getting any answers? Yeah, I got it. Okay, what is it looking like? Yes, they know about ammonia.
And there is a complaint from Sheikh that voice is not clear.
Voice is not clear. Okay. Is retracted. Okay, I hope the voice is clear. Third question is, what is ammonia made up of? Does anybody know the formula of ammonia? NH3, which means made up of nitrogen and hydrogen. Very good, very good. You know the structure of ammonia? Yes, some people know the structure of ammonia. Okay. All right. And finally, how many people got this joke? Do you know what the two dots on top of the end represent? Okay, let's see if anybody in the online audience. Does anybody know what the two dots on the top of the end are? It's a little joke if you know something. So if you have understood it, it's the structure of the three things are the three hydrogen atoms of the hydrogen. The two on the top is what is called the lone pair. If you know that much, this talk you know way too much chemistry, but you not need this talk. But just to warn you that it's okay if you don't know it, no problem. Okay, so the molecule looks something like this, and it's three, and there are two electrons of nitrogen that are still by themselves not attached to any atoms. That's called a lone pair. Okay, so now combining nitrogen and hydrogen to make ammonia. It's a relatively simple equation. Take nitrogen combined with 3 molecules of hydrogen, N2 plus 3H2, H2 is hydrogen, N2 is nitrogen, you get 2 NH3. What's this? Why such a big deal about such a simple reaction? Okay, what's the big deal about it, and why am I getting a talk just about this one particular reaction? And that is because nitrogen is essential for life. Okay. Especially organic compounds containing nitrogen. Simplest ones are amino acids. Amino acids with amino group is NH2. Amino acids combined together to make proteins. Proteins, everything in the human body. A little other slightly larger molecules. You have what are called nucleoside triphosphates. You have adenosine triphosphates. That's the sort of currency that is used by the cells, energy currency per cell. The cell pays for whatever it does in units of ATP. And of course, nucleic acids. So if there is one particular thing, I mean, if you have chemistry, probably think organic chemistry is all about carbon and hydrogen, which is the benzene structure, which is the ring-like structure of carbon and hydrogen. But there are many, many rings which have nitrogen in them. So there are rings which have one nitrogen in it. The most important ring is a 6-membered ring with 2 nitrogens. These are the pyrimidines, what you see on the right side here, the pyrimidines. And to the pyrimidines, you can attach another 5-membered nitrogen, which also contains nitrogens. That's called an imidazole purine acid. When you combine these two, you get the purines. So the purines and the pyrimidines are an extremely important class of molecules. Why? Because you're attending and cytosine and thiamine plastic depending on the DNA or RNA. These are the 4 sort of things, big acids which make up DNA and RNA. That's what makes up most of us and everything else on it. Hence, life needs to get nitrogen. We need nitrogen for life. Now, unfortunately, nitrogen gas is not very reactive. I mean, it's the most plentiful elemental element by which can get oxygen on Earth. 78% of our atmosphere is nitrogen. But N2, two N molecules, I mean, atoms come together with a triple bond, and it's very difficult to break this bond. Which is why you somehow need to convert that nitrogen into useful compounds. And this process is called nitrogen fixation. Okay. And by the way, the reason that the nitrogen bond N is so stable is also why in any explosive they have nitrogen. Nitroglycerine is what makes dynamite, trinitrotoluene, 3-nitrobutadiene, and all these explosives generally azides, they have the nitrogen. Because the nitrogen loves to leave whatever there is and form nitrogen into and go. Then three bonds together, triple bond, very, very stable molecule. So anything else from which it can break up, so nitrogen is a very useful. Now, by the way, these structures of purines, the purine structure I told you, you notice in this thymine and uracil, the difference is in one position you had a hydrogen here, the other one you have a methyl here, CH3. Okay, that's the only difference. Okay, and this difference can give you remarkably different properties. And the purines, you have noticed the same strength structures in reverse now. The same 6-member plus 5-member ring. Two very common compounds that you probably see. One is theobromine, which gives chocolate its flavor. The other is caffeine, which is coffee. Okay. Again, these are both purines. In one case, there's a hydrogen. In one case, there's a methyl. But you know the taste of chocolate. Okay. But here is again a purine that you encounter as a food item. Now, so if I want to make these very large compounds that biology needs to, run life, you want to start with small nitrogen compounds and organic nitrogen compounds. You require this to make the larger ones. And thankfully, evolution has ensured that there are some microorganisms, they are called diazotropes. Azo, by the way, is another name for nitrogen. So you will have azo is nitrogen elements, and you have azides, anything that A, Z, azo means there's some nitrogen. Okay. So there are some bacteria like azotobacters, azoto is again nitrogen. There are other things, archaea, another family. All these guys, they can take atmospheric air, nitrogen, and convert it to oxygen. Okay. And typically, these bacteria also have symbiotic relations with plants. So, if you've done any biology, you may know root molecules that fix nitrogen. So, on the roots of many plants, especially leguminous plants, beans and peas and things like this, there are structures on the root where bacteria live and they fix the nitrogen. And traditionally, what happened is all these plants, people have figured out that these plants enrich the soil. Okay, so you grow some of these legumes. Next time you can grow a rice or wheat or something on it. Okay, that takes up some of these nutrients. You can again grow these leguminous plants again. When they die, they give their nitrogen back in the soil. This is how it was going on for a while. But this is not a very effective way of supplying the nitrogen that the plants need for growth. Hence, you really want to make lots of crops, lots of things, there's a good way part to this fertilizers, which contain your nitrogen. That will come. But remember that nature has figured out this process of converting nitrogen into air to something useful using enzymes at room temperature. And enzymes are little protein molecules that are like, they help reactions happen quickly, they're catalysts. Okay? And the hero of this thing is this large molecule, this is called a nitrogenase, it helps fix nitrogen. And all these enzymes, at the heart of them, have a few atoms of transition metals. So all these enzymes have iron and molybdenum. In some cases, vanadium. But you need a few atoms of these. This is the typical structure of these large proteins. Hemoglobin has an iron in the middle. Chlorophyll is magnesium in the middle. So all these things have a metal ion that's doing the stuff. Okay. But this is nature's way of doing. Now, and hence, if you look at By the way, all images unless mentioned are from Wikipedia or Wikimedia Commons. I've written that on slide 1. So this nitrogen fixation cycle is very important. You have atmospheric nitrogen that comes to the plants, they live and die, and whatever happens, somewhere in school biology comes to the nitrogen cycle. So we grow crops, we need crops for food, which means we need fertilizers, which means we need nitrogen. Okay, so far. Now, why is this process such a big thing? Because today, more than half, perhaps 80% of the nitrogen atoms in you came from a synthetic industrial chemistry process, the Haber-Bosch process. This is perhaps the most important chemical reaction that has been developed in the last 100 years. It was developed in the lab. Nature has developed. But developed in the lab, more than half the atoms, depending on where you live, in some cases, 80% of the atoms are artificially sort of not pushy, but they came from a synthetic chemical reaction that was made by this Haber-Bosch process. Okay. And the availability of synthetic fertilizer is what saved humanity from famines. We could grow crops. The availability of food around the turn of the century, 19th century, 1910, 1920, the availability of fertilizer, etc., synthetic, is also the start of the world's population starting to explode because there is food. Right? So it's also the detonator of the population explosion. And ammonia, apart from taking fertilizers, is also the main product to make. See, nitrogen is not reactive. You want to make nitrogen containing anything to start. Okay, whether it is nitric acid, whether it is plastics, whether it is process, whether it is dyes, the new thing which people are thinking about is ammonia as a fuel. Okay, you can burn ammonia out. It's a liquid. Ammonia has 3 hydrogens. It is very difficult to compress hydrogen and liquefy it. Maybe using ammonia as a storage for and the way to use it as a hydrogen storage is one thing we are looking at, because ammonia is easily liquefiable and transported, etc. We work with ammonia for years, we know how to handle it. Okay, and burning ammonia is hydrogen will not get CO2. Okay, so people are looking at that as fuel in the future, maybe, and it is the second most produced chemical in the world. In 2021, 235 million tons per year produced. Almost a little less than a ton a day. Okay. This is the most produced chemical in the world. Any guesses? This is the most produced, like synthetic chemistry produced chemical in the world. Anyone online want to guess? Please write it on the chat box. We'll give it 30 seconds. Ammonia is the second most thing. Ammonia has 235 million tons per year. The number one around 2021 we had 250 or 260 million tons per year, not much more than ammonia. And has always been said, if you want to look at how well industries the country is doing, look at how much of this chemical it makes. Now, what's carbon dioxide anymore? It's become suddenly the bad stuff. Cement. Good, but it's not cement. It's sulfuric acid. Okay, number one is sulfuric acid. So this Haber-Bosch process for nitrogen fixation obviously has the names of Haber and Bosch. And as you will see, there are lots of other people. Now, going by the times it happens, it's basically lots of white men, but that's how the story is. Okay. But there are other people, there will be capitalists, they be less as they are foreign dance, a lot of people, and you can see lots of people with NP after them, NP means they got Nobel Prize. Okay, so the people connected with ammonia, there are 3 direct Nobel Prizes, Haber, Bosch, Hertel, but there are also some indirect people connected with ammonia who got Nobel Prize. So lots of Nobel Prize stories also in this. By the way, the Nobel is thanks to nitrogen stability, right? The Nobel is thanks to nitroglycerin, and nitroglycerin explosive. The reason explosives are all explosives are basically nitrogen. They depend on the fact that the N triple bond is very stable. You have something you want to decompose and become N triple bond eventually. Okay. Now, if you look at this picture of this thing, we've added a bit of thing next to the reaction, which is a value of how much heat is liberated. Don't worry if you know what delta is not is. If you see this as minus 45 or something, you're good. That's because they look at it as half and 2 plus 1.5 give you 1 mole of That should be 45. This reaction, the thing is 91. The minus means it's an exothermic reaction. Heat is coming out. Okay, that's all you need to know. It comes out. Now, if you look at the process, the main place where it happens is 450 degrees centigrade hot and 300 bar, 300 atmosphere pressure. The atmosphere, the thing has to be compressed to 300 times atmospheric pressure. And we need a catalyst. And this is why it's not easy. Now, in the last 100 years, the industrial ammonia has definitely changed the world. But we have a restriction. It's okay. But I hope the online thing is fine. Should we try and make this or it's okay? It's okay, right? All right. So there is a very nice paper, Nature Geoscience, that they came up first 60. They had something called how ammonia changes the world. And one very interesting graph, and a bigger one, is this, where they look at what would have been, this is world population going up from, this was the slope for a long time. Thanks to fertilizers, it goes up like this. I mean, you make plants, whether you eat plants or cows eat plants and you eat cow, it's eventually, you need the nitrogen. So without the availability of the Haber process, this would be what your world's population would be. Now we are on that line because we have the fertilizers. Okay, it's a very nice, it's available open source. You can Google it and you'll get it. Okay. However, I have story at the beginning. So let's see the origin of ammonia. The symbol for ammonia, NH3. But in the past, that's the symbol for ammonia. That's the symbol for Ammon. Okay, the Egyptian god. Ammon looks like this. Monkey hairstyle. Usually people or whatever. Blue ammonia. We buy blue ammonia. And there is a temple of Ammon. This is the one picture I could get. This is probably a reader start. There's a temple of Ammon in the Suwa Oasis near the Egypt border. Okay. And this temple is sort of one of the really important places. So everybody who wants to do anything will go there first and pray to Ammon or Ammon. And Alexander, before he decided to go and conquer the world, he went and sort of took permission from Ammon, the deity. And because he decided he was going to become a bhakt of Ammon, Egypt said, take us from Ammon to fight this. Okay. So now, obviously, how will people come to this temple? There's no trains and planes and cars those days. Typically, there have been somewhere in Egypt that they are born. Okay, so it's camels. Okay. So these camels, they will do their job. Okay, so there's a lot of camel dung all over the place. And there are people, and this is something which earlier nobody wasted, whether it is animal excrement, whether it's gobar, whether it is human excrement, whatever, it was put back into the field because it has nitrogen. Today, what you do, you flush it down with 100 liters of water, and then worry about making fertilizer. Okay, so just realize that the way we treat whatever nitrogen is made biologically is making matter. But in those days, people used to collect this. There were salts available then, and Pliny, who is a guy who wrote this natural history book. There's somewhere, we don't know exactly the date, but we know he died in the explosion, which is 77, which is 79, 78, 80 or 79, 80 or something. But the book must be written for this. He had called this salt of Ammon. The salt available near the temple of Ammon is sal ammoniac. Maybe he had not identified correctly, but by the 15th century, there are lots of alchemy books, the standard textbooks. These are all reprints. They are all books which mention sal ammoniac and its properties. So this is ammonium chloride. Okay? And Joseph Priestley's book on experiments and observation of different kinds of air, which is a 1774 book, he definitely talks about alkaline air. Alkaline air is ammonia, which is made from ammonia. Okay, so we know ammonia. So ammonia gets its name from the temple of Ammon. How do we know it's hydrogen? That we know in 1785, and there's then the lake. What he does, he exports ammonia-based. Okay, and that's also he decides that this is composed, he gets the water and he decides that this contains 2.9 parts of inflammable air and 1.1 part of scale of 3 to 1. Okay. Getting it there. Now, Daniel is also important because he's one of the early guys in chemistry who works on the idea that equations do not necessarily become A plus B equal to C plus D. It could also be reversible reactions with the concept of equilibrium. That is something which he also worked on. Now, if you don't have camels, birds, there's another thing called guano. Guano was very important in the world for a long time. Guano is these deposits, a bird nest. You can see birds with a nest, especially in islands of the South America, both islands in the Pacific, etc. There were lots of these birds which had this bird nest. The bird nest was right because of the bird's nest. And this is a very, very rich source of fertilizer, contains NPK that plants need, and it was called the white gold of the seabird. Okay, and this was essential for the production of fertilizer as well as gunpowder and nitrogen. Okay, and wars have been fought for the control of the coast of South America, Chile versus Bolivia, Chile versus Peru. All these wars were fought because of the important control of these islands of the coast which had these birds won. Okay, the US passed the Guano Act. Why do you think the US has all these tiny islands in the middle of the Pacific? They took them all because they wanted them for guano, for fertilizer, for nitrogen source. Okay, that's why you look at the map, you find all lots of tiny islands, Midway, this, that, all these islands are there in the Pacific, owned by the US right now. Okay, because they are totally over because of guano. And you may have remembered this. Remember what is the 3? Right, 6 plus 5. Remember, right? This is one of our bases. This is what? Guanine. Came from where? Guano. Okay. So you study ATCG, your base pair, etc. The G comes from what shape? Nature does it another way. Lightning. Lightning bolts are one of the rare natural phenomena where there is enough energy to break the nitrogen. And there is oxygen in the air, and this forms various oxides. So you can form some nitrogen oxides. Eventually, there's rain, it forms some nitrates, and that goes into the soil. Very small part. Okay, but this is a very small thing. But people figured this out, and they said, hey, now we have electricity. 19th century, now electricity. Can we use electricity to combine and get do nitrogen fixation? So the next person we asked is complete Davy. Davy's lab and all that stuff. But Davy is kind of the pioneer of electrical stuff and electrochemistry. Discovered a lot of elements by electrolyzing things that happens, and he electrolyzed distilled water in the presence of air and had constant amount of. Okay, and this was like a particular way, low currents, and there is the air has something to do with it because when he does it in a vacuum and distills water, he actually has it. But with the air, it's not as and it's very, very small. People try it. Even in 1922, they were trying to do it. Even at 1 ampere current, 1 ampere, they're getting something like a few milligrams of ammonia. Not that. Okay. So then there is a next, the first sort of industrial process which is described is something called the Berthelland-Hyde process. They don't make ammonia as such, but they are trying to do nitrogen fixation. At the end of the day, ammonia is very nitrogen. Now, this is something, and I cannot make the idea comes from Cavendish, the grand old man. Cavendish in 1785 has this paper. This remember that this is old English. F looks like F. Okay, whatever. So, in a paper printed in the last volume of philosophical transactions, I gave my reasons for thinking about, and this is the time when this phlogiston theory is happening, etc. And he said that he is doing some electrolysis, and the liquor when you go about smelled evidently of nitrous acid, and we evaluated, got some salt, etc. If it is acid, nitrous acid, so he's able to make nitrous acid, etc. by electrolyzing things. Okay. Now, this gets used by two guys in Norway. There is Christian Berthelland. He's actually a physicist. He's not a chemist. He's worked on aurora. He's worked on the solar storms and solar magnetic fields and interaction with the earth, etc. He had an idea that he would use electrolysis to do this in a way that would be feasible. Of course, scientists alone are not enough. Luckily, he found a very smart engineer, Samuel Ide. Samuel Ide was the guy who made this. This is the reactor outside of the place is Bhutan in Norway, and this itself is a 3 megawatt thing. So you have two copper tubes who actually like one tube inside the other. There's an electric arc struck between them, and so you get a plasma which has a temperature of 2000 degrees. You pass air through it, you get 4 to 5% of nitric oxide because of the plasma, and then the nitric oxide you can convert to nitric acid, nitric dioxide, nitric acid, etc. Now, this process it needs a huge amount of power to create this plasma and electric arc. And this is how Norway gets into hydroelectric power. This is one of the things that actually, they have these fjords from where they get waterfalls, they get something. And Samuel Ide, apart from making this process for fixing ammonia, starts up a company called North Hydro. And North Hydro is one of the biggest players in hydroelectric. This Buchan facility eventually they don't make ammonia or whatever, they don't make nitric acid, but they have it's near a hydroelectric power plant, they have huge amounts of power available, right? And this doesn't require coal to be brought from somewhere, it's hydropower. And this plant gets bombed like crazy in World War II. First, both sides bombed it. When after the initially the Germans bombed it, then when the Germans took over Norway, the Brits bombed. Okay, why? Because they were using electrolysis to produce deuterium. They were producing heavy water. So this was one of the first heavy water plants as well. Okay. Eventually, North Hydro gets into they have electricity. One thing that means electricity is aluminum. They went into making aluminum and other things. But this was also one of the first heavy water plants. So lots of interesting stories that all start off with ammonia. Now we're going to have something that comes to the story. Wilhelm Ostwald, we have got Ostwald process. Right? Ostwald is a pioneer of physical chemistry. He gets a Nobel Prize in 1949 for his work on physical chemistry, but in the middle, he developed a process for the manufacture, cheap way to manufacture nitric acid from ammonia. Okay? So you take ammonia, you oxidize it with a catalyst. Remember, you get nitrous oxide plus something. You react the nitrous oxide with oxygen, you get NO2 water, you get nitric acid, NO can go back, you get it freeze. This is the Ostwald process. Patent said 1902, improvement in the manufacture of nitric acid, nitric oxides, so you get US patent, British patent, etc. So he patents this process. So now, if I have ammonia, I can make nitric acid, but we need ammonia. The first real process that is done on the worldwide scale is something called the Frank-Caro process. So this is Adolf Frank, Nico and Caro. They do a very intense way of doing this. They start with calcium carbide, which is the same thing using carbide lamps, water, you get acetylene, which is in the lamps. They heat it up to nitrogen at 1000 degrees, it forms something called calcium cyanide. Okay, and that when you add water to it, gives you ammonia. So they make these huge things, huge ovens in our world, and it's like in Norway, made very energy intensive, but we pick up 1000 degrees. But we could make ammonia, and before Haber and come on the scene, this is the only process to make ammonia at a reasonable scale. But still, the world was still making 100,000 tons or something of like industrial scale process, the first industrial scale process. Then we come to another pioneer of the game. They may have not done some amount of history. This is a guy called Lipsky. Okay, this is only Louis Le Chatelier. His dad, Louis Le Chatelier, is a metallurgist. This guy is only here, and he's trained as an engineer. But like some engineers, they decided to like science. So he decides to teach chemistry. And he is most well known for something called the Le Chatelier. For Loesch-Chatelier principle, you can discuss it in many ways. The thing is this: if you have equilibrium means things are happening this way, things are happening that way, and amounts are there. If you do something to change it on one side, the system will respond in a way to minimize that change. Okay, and a very easy example is to, because you're talking about nitrogen oxides, I chose this one. There are two bottles here. One is yellowish, one is brownish. This is a reaction of nitrogen dioxide gas, NO2. NO2 is a brown gas. But NO2 can also form N2O4. N2O4 is a yellowish gas. So now, this reaction of N2O4 going to NO2 back and forth can happen. There will always be some amount of N2O4, some amount of NO2. This is an endothermic reaction, which means heat is removed, it becomes cold. Now, if I add heat to it, what happens? The reaction wants to become cold, so the reaction moves to the right, so that you will get more brown stuff. If you cool it, it will move back to the left. So you can just see this idea of Loesch-Chatelier principle by a very simple example like this, and it comes everywhere in chemistry. You cannot avoid Loesch-Chatelier. Okay, and anytime you need to ask an explanation in 10th standard, because of Loesch-Chatelier, this stuff, yeah. कुछ नहीं मिला तो Loesch-Chatelier. Okay, are we having any questions on Zoom or YouTube so far? Yeah, take a break. Okay. The amplitude in the previous slide was deuterium. Sorry, it was heavy water. This was heavy water. Heavy water deuterium oxide enriched with amplitude. The amplitude was that of heavy water, which was one of the products of North Side. Okay. Now, Loesch-Chatelier, one of the things he did was he tried to make ammonia. And okay, first thing, let's apply Loesch-Chatelier to see what conditions we expect. Okay, you have a reaction where nitrogen plus hydrogen gives you ammonia. Remember, heat is put out of this reaction. It's exothermic. Okay, and you have 4 volumes of gas on this side, you have only 2 volumes of gas. So the volume of the gas is going down. So what do you think will happen to this? If I want to make more ammonia, I want to push this reaction to the right. Should I increase the pressure or decrease the pressure? Let's give online audience a chance to write. Should I, based on Loesch-Chatelier, means if I'm pushing the system in one way, do something to minimize the change. Okay. So if I apply pressure, what happens? It will try and minimize the pressure, which means make things less. How can I make less volume by making ammonia? There are 4 volumes on the side, 1 volume on the side. So it's very clear that this kind of reaction, high pressure will help you. Yeah? Okay. Now this is a reaction that puts out heat. If it puts out heat, what do you expect? Right? Unfortunately, it's not simple always. It is there, but you still need some. Now, in 1901, Loesch-Chatelier almost had it. He has the Haber conditions. He has almost the Haber conditions. He is trying to get, he knows he needs high pressure. So he goes up to 200 atmosphere. He has an iron catalyst. He has 600 degrees centigrade. Unfortunately, he has contaminated his hydrogen and nitrogen or contaminated the leak of air and his apparatus. Okay, there was a devastating explosion in his lab, and he decided that I'm not going to work on this anymore. And after that, in his memoirs, he wrote a book later on, The Methods of Experimental Science in French. So you can see here, de la méthode science expérimentale. And he says that I let the discovery of ammonia slip through my hands. It was the greatest blunder of my scientific career. I should have realized the synthesis 5 years before. So Loesch-Chatelier came very, very close to finding out the conditions to make it. Okay. So now around what is happening around the turn of the century, this is around the 1901 that period, 1895 to 1904. At this point, thermodynamics is still coming up as a field. Right? We are trying to understand how temperature, pressure, volume, all these internal energy, all these things, what it is. And this there are people not there for they figure out the theoretical thing, which is around 50 years. For Boltzmann at 46, this is like half N2 plus 1.5 to 1 and H3. This number is around 50%. Now, you know, on heating the gas, it tends to decompose. Okay. But there is a guy called Devi. In 1865, he said that you continue to put sparks and decompose ammonia. Ammonia. Okay. Now, Ramsay, who was working on gases, Ramsay is the guy who argon, all the gases. He also worked on it. They were passing a mixture of trihydrogen over iron filings in a glass tube. Can't detect it. No appreciable quantity of it. There's another guy who in the 1904 says that, you know, I cannot decompose ammonia by heat because there's always some remaining in it. And Ramsay, of course, he was doing an experiment, but unfortunately, one of the glass things they blow up. There's a problem. I picture glass paper. And Ramsay, Haber read the 1884 paper and decided, look, maybe there is something about ammonia, hydrogen, nitrogen, or equipment. How do we do this? So, enter Haber. We start the hero of the Haber-Bosch process. This is part 1 of Haber. This kind of the most different chemists the generation around that time. Between 1900 and 1905, we have 50 papers. Okay. Now, Haber comes from a family. Unfortunately, his mother passed away when he was born. So somehow his family had a big fight with his dad or him, whatever else. He told us that, look, the era of natural ties over as synthetic ties wasn't big. Eventually, they made synthetic ties. They stockpiled a lot of calcium hydrochloride. This is like it. Okay, when the cholera epidemic was coming, this is one thing which would work. Unfortunately, it never came to Germany. There are tons of unsold wheat, etc. And the dad was saying, you're no good for business. So we decided, I'm no good for business. I'll become a 1894, he was the prof of the University of Karlsruhe. And in 1904, he gets a request from the Austrian chemicals company there in Vienna to investigate the synthesis of the elements. And he read through all the literature and he thought that, you know, all these people, they have a prejudice in hard make ammonia. And he said, look, this must be something at equilibrium. He knows that the other group at that time, like Nats, is also working on this. He wrote to him, he was trying 30 atmospheres in that 30-75 range. He wrote to Nats, saying, look, this is it. So the other part is alternatives. Now, this guy is the guru of thermodynamics. Nernst law, the third law. Nernst disagreed publicly with Haber. Okay, and according to Nernst's calculations, Haber was wrong. Once is the thermodynamics guru, he's saying Haber was wrong. He challenged Haber to a public debate in 1907, and in this he ripped apart. He just destroyed Haber's results and sarcastically told him, you know what, you should have. And Haber was saying, "Nothing to पंगा लिया है तुमने, दिखाता हूँ." So Haber decided, yes, I will use higher pressure. And at that time, he had an assistant, Rossini. His story comes up next. So we will take this ammonia work seriously because I have to now have पंगा with Nernst. Okay. So Robert Rossini is a Brit who has finished his studies, and he was in those days. Remember, Germany is the mecca of chemistry. What is chemistry for Germany? Heidelberg, Karlsruhe, all these are places. And he was going to write to these people as advice. Then he heard this mistake, and he said, "No, go to Harvard." So this Brit, just before World War I, lands up in Harvard. Okay. And he looked at, so they revised, they looked at all their data, they realized, yes, we have got wrong somewhere, let's do this again. And he started experiments at high pressures, Now the pressure is so high. Normally, what you do, you have a cylinder which contains gas at high pressure. You have a regulator to reduce the pressure, and then you use it. You need such high pressure that you can't get gas into the cylinder. But how do you control it? So he, with another forgotten figure lab technician now, he designs this valve, okay, which is a very fine valve, etc. Just directly on the cylinder and get gas at that pressure and control flow. This is the first needle valve, real needle valve very high pressure, and this is now a standard industrial needle valve. Anything in industrial flow, the needle valves, this comes from again the history is ammonia. Now, Rossignol, every patent of Haber, every patent is, this is 1911 US patent, Fritz Haber of Karlsruhe and Haber Rossignol Berlin, Germany, given to BASF. This is partnership between solar fabric and BASF. Again, this is process of making ammonia. Another patent 2016, F. Haber and R. Rossignol. Okay. By 1908, these guys had a paper published. They published their new results. In this case, solved all their problems. They had now solved whatever learned task. They had done it. More than that, they had built a setup that was giving 100 milliliters of ammonia. They have made it that way. 100 milliliters. Get some okay, high pressure. But okay, not here. If you look at these patents, maybe you can even read it here, that the patent says that in a catalytic agent consisting of or containing uranium. Okay. Now, Haber's original patents are all based on uranium and oxygen. Why? Because they have access to it. Why? Because the electric bulb is still not the power. They are still using Petromax lamps. You see in gold Petromax lamps, which have a mantle. The mantle had oxides of sodium and oxygen. There was one company called Auer in Germany, made these lamp mantles. They had highly divided oxygen. So he had something. Now, Alvin Hitash is a guy who was a chemist hired by BASF in 1904. BASF is very big, already a big company in Germany, right? In 1904, BASF also wants to work on this before. They will eventually buy everything, they will get the Haber patents, but they also want to work. And BASF already had done a lot of work in chemistry, they had a lot of patents, they already got those other people worked out. So they had a lot of patents, they had patents on catalysts. They said Rossignol will try all these catalysts. Titanium nitride, aluminum metal, you add some sodium chloride, something, add some calcium carbonate, it helps, add barium, it helps. They are trying to do all these things with their own catalysts. Then in 1909, BASF, the team from there, and Haber-Bosch, who is the leading scientist at BASF, they visit Haber's lab. Alvin Hitash learns about this osmium catalyst, and he thinks, the world is having a hundreds of osmium. You can't make worldwide process for large scale amounts. I have to do something else. Do you remember the periodic table? You don't? It is iron, ruthenium, phosphate, that group. So he's going to try catalysts from that group. Okay. And Alvin Hitash did 6,500 experiments with 2,500 different catalysts. Okay. And there is a patent by Haber-Bosch, Alvin Hitash, and others of this is assigned to BASF. We have experimented with iron catalysts and found that the lower form of iron, including the iron which is sold as purest or guaranteed pure, are impractical for me. But we have now discovered a way of making ammonia with a new form of iron that is very dangerous. So Alvin Hitash is the guy who comes up with the catalyst. Okay, Robert Rossignol is the guy who actually does the Godagiri for making this ammonia thing. Now you can make ammonia. It's important enough that the Nobel Prize in 1980 is for the synthesis of ammonia from its elements, and it was only 1%. Okay, I think Rossignol and Hitash played, really important roles in this. But Haber was the thing. He gets it. Because anyway, that's history. So Nobel Prize, you can go to the Nobel website, but it's Haber, so this is the moment. Still, we are doing 100 million liters a day. Now enter Haber-Bosch. It's a Haber-Bosch process. Okay. So Bosch is a pioneer in high pressure chemistry. Chemistry at high pressure. By the way, this guy is the nephew of Robert Bosch. Robert Bosch made the first class particles, and now you see Bosch, whatever the appliance company, that's Robert Bosch. Okay, this is Carl Bosch. Carl Bosch is the nephew. Okay. So Bosch went and met Haber. He understood that this industrial scale up is not your thing. We were doing in British House, give the patent, etc. I think we do it in British House as a reactor is there, and as they say, the rest is this. Now, remember, it's not easy to design compressors and compressor gas practice. It's not easy to design a vessel that withstands the pressure and high temperature while doing the actions and scale it up. And that is what this guy is good at. He takes it and in 1911 starts a plant in Ohio. Ohio is just putting and that is 7,000 tons a year. First plant from the lab is 7,000 tons a year. Soon after, they take another plant in China, which is 33,000 tons a year. By the end of World War I, 20,000 tons a year. Okay. And after he figured out, okay, now ammonia again, what is the next high pressure reaction I can do? That is to make, remember, Germany doesn't have oil. World War I started, there's no, Germany doesn't have access to shipping lanes are blocked. They can't import crude oil, they need petroleum. You can take coal under high pressure with hydrogen, whatever, and somehow try to convert it to. Okay. This process is called the Bergius process by another scientist, Bergius, who developed high pressure process. So he decides after this, I'm going to put the next important industrialized process that we need to make petrol from coal, the Bergius process. And the 1931 Nobel Prize is a prize given to Bosch and Bergius for their contribution to the inventions of chemical high pressure. Okay. Every person in the story is a, except the people like Rossignol you've never heard of, Vitash you probably never heard of, only heard of the others. A Bergius, I don't know. But how does nitrogen and hydrogen come together on an iron surface? That is something that nobody knew. How did Vitash figure it out? 6,500 experiments. The understanding of that comes very late. It comes in the 1979, 1980 by Gerhard Herzl. Gerhard Herzl is a professor in Berlin. He works on the role of potassium, XPS, what happens in interaction, iron surfaces, kinetics of nitrogen absorption, etc. And he figures out this entire pathway. And for this, Herzl gets the Nobel Prize in 2007, right now. Almost 100 years after Harvard did it in his lab. 1907, 2007, Herzl gets the Nobel Prize. So this is a fantastic story. We started off with the power, the first plant. This is the first reactor for ammonia being lifted up into position. This is at this point 10 tons per day. Today, 2022, new system being put in Saudi Arabia, 3,300 tons per day. Okay. Which country makes the most amount? China, followed by India. We make a lot of 7.9, almost 8% of the world's ammonia is more than the US. I don't know how I'm doing on time. It's almost, we have time. If you're interested, I can tell you an aside about the 1921 performance. Okay. Now, ammonium nitrate and ammonium sulfate are fertilizers. Right? So they used to make ammonium nitrate and ammonium sulfate, and they get this inside. And ammonium nitrate is hydrophobic. It absorbs water from the air. So what happens is eventually ammonium nitrate, ammonium sulfate sort of dissolves, makes some slurry, and it becomes like sticky and it comes down. So there are these 20-meter high silos, and it becomes a sticky stuff. And people have to take it out, and workers try and break it with with a pickaxe or whatever, to try and break it up. Okay. Remember, ammonium nitrate is also explosive. Somebody had this bright idea that this breaking with an axe is small. Why don't we make smaller pieces to ease their work, small charges of dynamite, or put in that ammonium nitrate silo to try and break it up? Yes, they broke it up. Okay. That is where that circle you see, that is where that silo stood. This is happening in the power, which is somewhere in central West Germany. The explosion was heard in Munich, 300 kilometers away. It blew off all the windows in a radius of 45 kilometers. Right? This is an explosion equivalent people today was like 4,500 tons of ammonium nitrate, 2 kilotons of TNT. Hiroshima has 15 kilotons. So this is like one of the largest non-nuclear explosions that ever happened. Ammonium nitrate is a very, very dangerous thing to handle. In the middle of the COVID pandemic, you remember there was a Beirut explosion, which was only 2,000 tons. And wiped out the entire port of Beirut. Okay. So, but this is the point. These were small charges of dynamite were used to break up ammonium nitrate. In today's world, you would ask, like, what were they? But apparently, they were not so stupid. They had done these studies in small amounts of things, in small bits of explosives to see whether they could break it up in the study, and it had worked. It had worked some, for some few hundred times that they've done it. Except they tried this in the larger side. And then they were history, I guess. Now, Fritz Haber is a very, very interesting character. He has a completely different side of it. Fritz Haber, who gave us the process for ammonia, prevented famine, etc., is also the father of chemistry. So, in World War I, a lot of people in Germany felt that they were really not responsible for this. They were on the many intellectuals, academic scientists signed what is called the Manifesto of 93, which you see over here, the original version. This is signed by Haber, not just Haber, it's signed by Pauli, it is signed by Bertzi, it is signed by pretty much everybody in that time in Germany signed it. And Haber famously said that during peacetime, scientists belong to the world. During wartime, the world. During wartime, he was one of these very, very patriotic Germans who decided that he will work with the gas. Okay? He worked on basically how they deliver chlorine on the ground and please chemical warfare in World War I. You won't be surprised that the scientists work on this. Okay? World War I was called a battle of the chemists. Don't worry, it's not, we can judge him today for giving something. But on the other side, in France, is another guy whom you've all heard of. The War of the Chemists. On the French side is Victor Grignard. Okay, for the Grignard, which they call the Grignard's agent, which is over here. Okay, this guy came up with phosgene, which is far more toxic. So, mustard, they were to detect mustard gas. So, all the chemists were working. Next, we can say that, but you have to look at it in their times and whatever happened. But this is Fritz Haber, a person who has done many things and has a very complicated history. Karl Bosch, for example, founded IG Farben. IG Farben was a company which eventually the Nazis used to make a lot of these chemicals that were used. He was extremely anti-Nazi. Two of his sons were married to Jews. They had to escape. And he eventually, I think, died out of depression or something. But so there are something. Now, today's concerns, the ammonia process are very different. This is not an area which I have experienced, but the Haber-Bosch process, 80% of the atoms come from Haber-Bosch process. It uses almost 5% of the world's natural gas because the easiest way to highly stressed natural gas, not very toxic. We don't have that much. Uses 2% of the energy. Everybody is worried about improving the energy efficiency and carbon footprint of ammonia manufacturing. So if you look at any results, CNN, the news, the Royal Society of Chemistry, the International Energy Agency, the ammonia, etc. Everybody is looking at how do you make green ammonia. There are lots of new technologies which may come up. As of now, it's still happening. Okay. Now, just to tell you why I am. This is my lab. I grow gallium nitride as a factor. And the one reaction that I've done for the last 20 years is taking trimethyl gallium reacting with ammonia to make gallium. For this, I use what is called blue ammonia. Blue ammonia is the purity grade. So this is 99.9999997% ammonia pure. Nobody makes it. We have RCF that makes tons and tons of million tons of ammonia. But that's they don't even know what very high pure ammonia. But this is what I do. And yeah, thank you. I hope I could tell you a little story about a simple gas turbine. I am happy to take questions. Online audience, once again, please put your questions in the chat and we'll try and take it. But yeah, that's the story of ammonia. I hope you learned something new about this rather simple compound that we unfortunately smell every time we go to a public toilet. Zoom questions, yeah, go ahead. I can stop sharing. Yeah, are there any online questions on Zoom or I can do it? Okay, nothing much here. So, yeah, just before we shut down the online thing, of course, you get for a chai. Chai. The online audience, unfortunately, you will get the chai of the chai and wine. You'll have to make your own chai or coffee or whatever. You guys wait. We'll have chai. We'll have a lot of question answers after chai. Are there any online questions? Just to tell the online audience again, the next chai and wine, December 4th at Prithvi, is on the history of Indian science, just before independence mostly. And after that, the mid-December session here at Uparil is about, it's the time, the week when the Nobel Prize is to be given. It's about the physics, the chemistry Nobel Prize. Sunday, 1st of Jan at Prithvi again is going to be the medicine Nobel Prize. Chai and wine. That's what's planned for now. And again, any last minute questions? Nothing. Okay. So then we will stop the live stream and come back to your questions. You can end the session.